Welcome to the third lecture for the introduction to power system. Today we start basic concepts in electric power system. You can get or contact me by institutional email haymanot@gmail.com and YouTube Ingeratube. Don't forget to subscribe, share and comment me to get more videos, and you can also get Telegram page K and Light. So for a power system, basic concepts of power system starts from a single phase power system powering single phase AC system. So the instantaneous power was absorbed by an electric load is the product of the instantaneous voltage across the load in volt and instantaneous current into the load in ampere. That means that the instantaneous power P of t is equal to the instantaneous power V of t times I of t, where V of t is equal to V max times cosine of omega t, V max cosine of omega t plus sigma, and the instantaneous current I of t is equal to I max times cosine of omega t plus sigma. That means, as indicated, this one. This is the instantaneous voltage, and assuming the load voltage is purely resistive load, there are different sorts of loads. From those, resistive load, inductive load, capacitive load, in general, RLC loads are there. And by assuming a load voltage purely resistive load, for a purely resistive load, the current into the load is in phase with the load voltage. That means a current in the resistive load is equal to the ratio of the voltage over the resistance, and the current into the resistive load is equal to I max times cosine of omega t plus sigma, which is measured in ampere, and the maximum, this R max is equal to the ratio of V max over the resistance R, the load. So the instantaneous power absorbed by the resistor is the product of the instantaneous voltage times the instantaneous current, where instantaneous voltage is equal to V max times cosine of omega t. That means V of t is equal to V max times cosine of omega t plus sigma, and the instantaneous current is equal to I max times cosine of omega t. Then when we multiply both, we get V max times I max times cosine of omega t plus sigma. Then note that in trigonometric identities we have cosine of 2 times cosine square x is equal to 1 plus 2 cos 2x, which is a double angle formula. Therefore, cosine of x, by letting x is equal to these values, then cos square x is equal to half times 1 plus cos omega t. Then substitute this amount into this position. We have 1 over 2 V max times R max times 1 plus cos 2 times omega t, since x is symbol as omega t plus sigma. Then finally we get VIR. This amount V max is equal to V times square root of 2, and I max is equal to I times square root of 2. When we multiply this one, we got Vi times square root of 2 the whole square, which is equal to Vi times 2. Vi times 2. Then substitute this value in terms of this position. We got this one, V times IR, which is the load is resistant, over 2 times this value 2, this one. Then times 1 plus cosine of 2 omega t plus sigma. Therefore, the instantaneous power PR of T is equal to the product of the voltage times IR times 1 plus cosine of 2 omega t plus sigma, which is for resistive load. So the instantaneous power absorbed by the resistor has an average value of PR is equal to V times IR, which is equal to V square over R. Since V is equal to the current I is equal to V max over R. Then substituting this value, we got V square over R, which is equal to I square R, which is measured in watt. Don't forget the unit, plus a double frequency of this value. That means this value is said to be double frequency and indicated as this one. The next load type is purely inductive load. For a purely inductive load, the current lags the voltage by 90 degree. So the inductive load, the current is equal to the ratio of the supply voltage over the inductance value. And the inductance IL, the instantaneous current in inductive load, is equal to the maximum current in inductive load times cosine of omega t and shifted by 90 degree, which is measured in ampere. Therefore, the maximum current in the inductor is equal to the ratio of the maximum voltage supply over the inductance of the circuit. And where the inductance in the inductive load is equal to omega times the inductor value, where omega is equal to 2 pi times the frequency, and is the inductive reactance. The instantaneous power absorbed by the inductor is also the product of the instantaneous voltage times the current, the instantaneous current in the inductive load, which is equal to the maximum of the voltage times the maximum of the current times cosine of omega t times cosine of omega t plus sigma minus 90, since the inductive load lags by 90 degree. Inductive load current lags the voltage by 90 degree. Then by using trig identities, we have cos x cos y is equal to 1 over 2 cosine of x minus y plus cos x plus y. Let x is equal to omega t plus sigma, and y is equal to omega t plus sigma minus 90 degree. Then by substituting this amount, you have 1 over 2 times V max I max cosine of 2 omega t minus 90, and finally we got this amount of voltage, only the double angle. So the instantaneous power absorbed by the inductor is a double frequency with zero average value. In the resistive load, we have V times IR, which is average value, and in the inductive load there is zero 0, 0 average value. Then the next one is general load, which is RS is what. For a general load composed of the resistive load, inductive load, and capacitive load elements under sinusoidal steady state excitation, the load current is of the form I of t is equal to I max, maximum of the current, times cosine of omega t plus beta in ampere. So the instantaneous power absorbed by the load is then the product of the instantaneous voltage times the product of the instantaneous current. So is equal to the instantaneous voltage is V max times cosine of omega t, V max times cosine of omega t plus sigma, and the instantaneous current in general load is equal to the product of I max times cosine of omega t plus beta. So by applying trigonometric identity, cosine of A, cosine of B is equal to half of cosine of A minus B plus half of cosine of A plus B. Let A is equal to omega t plus sigma and B is equal to omega t plus beta. Then when we subtract the value of A, when we subtract B from the value of A, we have sigma minus beta, which is this value. And when we add both two values, we got 2 omega t plus sigma plus beta, which is equal to 2 times omega t plus sigma minus beta. This is for the case of analysis, simplicity of analysis. Therefore, by multiplying this amount, then Vi, this is V times square root of 2, and this is I times square root of 2. We got 2 times Vi over 2, then 2 by 2 is cancelled out. Therefore, the instantaneous power P of t is equal to Vi cosine of sigma minus beta plus Vi cosine of sigma minus beta times cosine of 2 omega t plus sigma plus Vi sine of sigma minus beta sine of 2 omega sine beta by using multiplication rule of cosine angle. Therefore, the instantaneous power is equal to Vi cosine of sigma minus beta times 1 plus by taking common value Vi cos sigma beta in this case, and Vi cos sigma beta in this case. So by taking this common value, Vi cos sigma beta into 1 plus cos 2 omega t plus sigma plus Vi sigma beta is the other common value, then Vi sine sigma minus beta sine of 2 omega plus sigma. Then by letting I cos omega t is equal to the resistive current load and I sine sigma minus beta by Ix reactive load current, which gives P of t is equal to V times, since the value of I cos sigma theta, this value is IR, then we get this value times 1 plus cos omega t plus sigma plus, and by taking Ix, I sine sigma by Ix, therefore Vi x sine of sigma t. Therefore, this instantaneous power incorporates both active and reactive power. This one. This is the active power and this is the reactive power. So the instantaneous power absorbed by the load has two components. One can be associated with the power PR of t, which is real power absorbed by the resistive component of the load, and the other can be associated with the power which is reactive power and absorbed by reactive that incorporates inductive or capacitive component of the load. So by having this, we are going to analyze a complex power. What's complex power? A complex power contains both active and reactive power, which is measured by megavolt ampere. So the active power is the power that dissipated in the resistance, dissipated with in the resistance, and it uses the same formula used for DC voltage and current are magnitude, not the phasor diagram, which is the power reactive power is equal to the product of the current square times R, which is power loss, which is equal to the supply voltage square over the resistance, which is measured in watt. The other is the reactive power, is the power that exchanges between reactive components, either inductive or capacitive components. In the inductive component, reactive power is equal to the square of the current times the reactance, or which is equal to the square of the voltage divided by the reactance, which is measured in volt ampere reactive. So the formula looks similar to those used by the active power, but uses a reactance instead of a resistance. This one instead of this resistance. So for circuits operating in sinusoidal steady state, relay and reactive power are conveniently calculated from complex power, which is defined as let the voltage across the circuit element B, a voltage V at an angle delta, and a current into the element, the current at an angle beta. Then the complex power, which is symbolized as S, is the product of the voltage and the conjugate of the current. When we conjugate the current, the angle becomes negative. And the complex power is equal to the product of the voltage times the conjugate of the current. Then the value of V is equal to V sigma, and the value of current is equal to I sigma and conjugate, which is equal to Vi sigma minus beta, which is equal to Vi cos sigma minus beta plus Vi j sine sigma minus beta, where sigma minus beta is the angle between the voltage and the current, as said in this statement. For the complex power, a complex power is the sum of active power and reactive power. So for a real power and reactive power, P is active power, reactive power, and this is said to be power factor. So the magnitude of the complex power Vi of the complex power S is called apparent power. It signifies that the rating of the equipment, for example, generator, transformer, measured with this apparent power. So there is a relationship between real, reactive, and complex power. If we have given the magnitude of if we have given the value of reactive power, a complex power instead, we can calculate reactive and active power. The active power is equal to the magnitude of the complex power times cosine of the angle, which is the power factor. And the reactive power is equal to the magnitude of the complex power, which is apparent power, times sine of phi. Example: a load draws 100 kilowatt with a leading power factor of 0.85. What are the power factor, reactive power, and the magnitude of complex power or apparent power? So by having this question, we can calculate a lead, but we have given a leading power factor, and the power factor is equal to minus of the cos inverse of given power factor, which is 31.8 degree. Then apparent power is equal to the ratio of this active power divided by the power factor, which is 117.6 kilovolt ampere. Therefore, the reactive power is equal to the magnitude of the reactive power times sine of the angle, which is minus 62.0 kilovolts ampere. This is lagging power factor and leading power factor. The other one is power triangle. From the complex power expansion, the following can be stated. A resistor absorbs positive real power, which is the square of the voltage over the resistance, which is measured in watt, and zero reactive power. An inductor absorbs zero real power and positive reactive power, the square of V over XL. And a capacitor absorbs zero real power, and negative reactive power. Alternatively, capacitor delivers a positive reactive power. It gives direction of power flow. Consider the current and voltage of figure, this one, where a DC current is flowing through the battery. DC flowing through this direction. If the voltmeter and ammeter both read upscale to 100 value of A and 10 ampere, this current 10 ampere, the battery charges. The battery absorbs energy and it gives us 1000 watt. On the other hand, if the ammeter connection has to be reversed, it means if it's said to be plus and it's minus, if the ammeter can have to be reversed in order that it reads upscale with the current arrow still in the direction shown, which is minus 10 ampere. It discharges. The same is considered applied to AC supply relationship. This AC supply. This figure shows an AC system with an ideal voltage source with polarity markers to indicate the terminals which is positive during the half cycle of the instantaneous voltage. Similarly, the arrow indicates the direction of the current. The arrow indicates the direction of the current into the box during the positive half cycle. And by definition, the power absorbed inside a box is equal to the complex power is equal to the supply voltage times the conjugate of the current, which is equal to the magnitude of the voltage and current times cosine of theta plus J times magnitude of voltage and current times sine of theta, where theta is the phase which the current lags the voltage. If the active power is positive, real power is absorbed by the battery, and if the active power is negative real power is supplied by the voltage. Generally, we can determine the active and reactive power absorbed or supplied by any circuit as enclosed a box. This one. If the value of active power is greater than 0, circuit absorbs real power, and if the active power less than 0, circuit supplies a power. And if the reactive power greater than 0, circuit absorbs reactive power, and less than 0, circuit supplies. For a balanced three-phase system, three sources connected to three loads using four-wire system. Sources have equal frequency but different phases, and it have a phase shift of 120 degrees. Balanced three-phase voltages have same voltage magnitude and 120 phase shift. There are two possible sequences that are ABC and ACB sequences. For ABC positive sequence, and ACB positive sequence. So balanced three-phase circuits has in the current also have this amount. I am cos omega t minus theta. I am cos omega t minus theta minus 100, which is shifted by 120 degree and which is shifted by 120 degree. So the solution of a three-phase network under balanced condition is easily carried out by solving the single-phase network corresponding to the reference phase. The generator and load neutrals are therefore the same potential, so that the neutral current is equal to 0. Look this one. Neutral current is 0 since it's balanced. It's balanced, and the voltage at line EA is equal to the generator impedance plus the line impedance times the current in line 1. So the neutral impedance ZN does not affect the network behavior for a reference phase A. So the current and the voltage in the other phase have the same magnitude but progressively shifted by 120 degrees. Consider the K-square three-phase transformer part of the three-phase power. So if a transformer start connected as shown in this figure, the single phase equivalent, the three-phase circuit can be obviously represented by single phase transformer with primary and secondary permitting to phase of three-phase transformer. So if the transformer is star delta connected as indicated this one, star delta connected, which is replaced by equivalent star connected as dotted one, this one is dotted one, star connected. So when the load is balanced, the impedance of each leg of the star is 1/3 of the impedance of delta. Y impedance Z, YZ is equal to 1/3 of delta. The circuit, which is single phase equivalent, this one. Since both phase voltage and the line current shifts through the same phase angle from star to delta side, the transformer per phase impedance and power flow are preserved in the single phase equivalent. From your fundamental course, as you remember that to convert delta connected circuits to star connected, we have used this formula. Then R1 of the star connected is equal to RB times RC of the delta connected divided by the sum of the delta connected systems, RA, B, and C, and R2, RC are the like. So it may be noted here that irrespective of the type of the connection, the transformation ratio of the single phase equivalent of a three-phase transformer is the same as line-to-line transformation ratio. So to convert delta Y connection, or to convert line-to-line voltage into phase voltage, or phase voltage into line-to-line voltage, we follow these procedures. Therefore, VAB, the voltage, line-to-line voltage VAB is equal to the phase voltage VAN minus VBN. VAN minus VBN. And VBC is equal to VBN minus VCN. VCA is equal to VCN minus VAN. Therefore, VAN is equal to VRMS at an angle of 0, and VBN is equal to VRMS times at an angle of minus 120 degree. So delta connected source can be replaced by a star connected source using the phase voltage is equal to the line voltage divided by √3 over 30 degree. √3 times at an angle of 30 degree. Therefore, to get the line-to-line voltage from the phase voltage, we use VAN. VAB is equal to the difference of VAN minus VBN, and VAN is equal to VRMS at an angle of 0 degree minus VRMS at an angle of minus 20 degree. Then by using Euler's formula, we have VRMS e the power of j0 degree minus e the power of minus j20 degree. Then Euler said that e the power of some value x is equal to cosine of x plus sine of x if the number is positive, and if the number is negative, it's said to be negative. Therefore, VR image is the power of g0 minus the power of minus 120 degree is equal to VR image times cosine of 0 degree is 1 minus cosine of 0 sine of 0 degree is 0. Therefore, VR image minus 1 minus e the power of minus j20 degree is equal to cosine of 120 degree minus j sine of 120 degree. Then it is minus 1 over 2 and it is minus root 3 over 2. Root 3 over 2. Then multiply by this one and this one becomes positive. Therefore, the RMS value, the line-to-line voltage of A and B is equal to the RMS voltage times 1 plus 1 over 2 plus j root 2 over 2. Then by taking common 2 and 2, we have 3 plus j root 3 over 2. Then taking common root 3 in front of the RMS voltage, then root 3 times RMS, then this is root 3 times root 3 which gives 3 and plus root 3 itself. Therefore, it is equal to the root 3 times the RMS times tan inverse of 1 over 2 over root 3, which is 30 degree. Therefore, the line to line voltage AB is equal to root 3 times RMS voltage times at an angle of 30 degree of that of phase VAN and VPN. So there is like that. This other. In turn, line to neutral voltage VAN, VRMS 0 degree, VPN minus 100, which is shifted by 120 degree. Then line to line voltage is equal to VAB times RMS voltage times 30 degree, VBC RMS voltage at minus 90 degree, VCA RMS voltage times 150 degree. So delta Y transformation, to simplify the analysis by three-phase system, delta connected load can be replaced by star connected load, with delta connected can be replaced by Y connected sources like this one. So line to line voltage in terms of line to neutral voltage is equal to this amount. Thank you for watching this three-phase circuit. Don't forget to subscribe, share, like, and comment for more videos. Thank you again for watching.